in this session we will be closely observing the working of different fundamental blocks of a DC regulated power supply. For this we will be employing NVIS 6003 comprehensive power supply trainer. This is a self-contained unit right from transformer to the load. There are in fact 4 blocks here. You can see this is the transformer section, this is the rectifier section, this is the filter section, regulator section and load section. In the load we can have this variable resistance for load regulation study, and we have got a bleeder resistor here that can be employed for line regulation study. We are not be going for load regulation or line regulation study. Rather, we will be observing the operation of transformer, the rectifier, the filter and the regulator. You can see this is a step down transformer. On the primary we can have 230 volt AC. We are having 230 volt AC, and at the output we are having that is on the secondary we are having 18018. That means this is a center tap transformer. In the rectifier section we have got a full wave rectifier that is made up with the 2 diodes D1 and D2. Next we have got full wave bridge rectifier where we have got 4 diodes D1, D2, D3 and D4. Now see, these diodes are given and the circuits have been made internally with the mimic that are showing what is there in that block and how the connections are made. Only the external terminals where we have to make the connections have been provided. Now you see in the filter section we have got an LC filter and a pi filter. So for the regulator section is concerned, we have got 2 Zener regulators, one for 10 volt, other for 5.6 volt. Then we have got 3 IC regulators. One is 7812, other is 7912 and the final one is LM317. You see this 7812 is a positive regulator. This 7912 is a negative regulator and 317 is a positive variable regulator. Now this is a special case. In these two they are fixed value regulators. This is a variable regulator. However, remember this we can have also negative variable regulator. In that case it will be LM337. Now we will be specifically look towards 7812 and 7912. This 7812 can give you a positive fixed voltage or regulated voltage of 12 volt at the output. There is a complete family of such IC voltage regulators. There can be 7805, 7806, 7809, 7812, 7815. In all cases, the last 2 digits they signify the fixed value of regulated voltage, and the first 2 digits that is 78 that signifies it is a positive regulator. If it is 79 it signifies that it is a negative regulator. Okay, now you see that this LM317 it gives you a voltage not from 0 volt but to the you kindly check it out, it is 1.5 volt. From 1.25 volt onwards it gives you the variable voltage. Now you see here we will directly check with the potential and then the waveforms also. You can see I have fixed the multimeter to DC voltage. Center I will be using the connecting the common terminal of the multimeter, and here positive terminal. You can see, sorry, this should be AC, and you can see here this is 19 volt. Fine, that is what we were expecting, somewhere around 18 volt. So this is 19.1 volt. All right, I'll remove this, and then I will be introducing the full wave rectifier in the circuit. Now out of this rectifier, at the output of this rectifier, we will be having a rectified output, that is a DC voltage. Okay, let's connect the rectifier. So we are connecting the rectifier. Better to stop the circuit, and we have to connect the load. Therefore I will be taking this center terminal to the load ground, and output of this full wave rectifier to the load. Okay, now we will be checking what is the output voltage of the full wave rectifier. So now we can simply go for DC, and I will be having the ground connection here at the center tap of the transformer. Then you can find I have connected to the output of the filter, and you can see the output value from the full wave rectifier is near about 17 volt. Okay, that's good. Now we will be connecting this output of the rectifier to the pi filter. So I am connecting it here. Now I will be connecting output, that is ground of the transformer, to this filter section, and then from the filter I will be filter ground I will be connecting to the load, and output of the filter to the load. Now we will be checking the voltage at the output of the filter. You can see it is 24 volt, and at the load again it is 24 volt. Now you can see at the input of the filter it is 24 volt, at the output of the rectifier it is 24 volt. Now you can see, if I check it at the input of the rectifier, it is 18 volt and 18 volt at the input of the two diodes. Now this is an assignment for you to find the answer, that why the output of the rectifier section is having 24 volt. Okay, now I will be simply using this output of the filter to the input of the positive regulated supply. Now remember that whenever we are using a positive regulated supply, this package, then pin number 1 is the input, pin number 2 is the ground, and pin number 3 is the output. Whereas in case of negative regulator, that is 7912, remember that pin number 1 is ground, pin number 2 is the input pin, and pin number 3 is the output. Many times we do silly mistake while doing the connection. So now we are giving the output of the filter to the positive voltage regulator. You can see that output of the filter is connected to the positive voltage regulator, and ground is connected to the ground of the regulator. Now we will see what is the voltage at the output of the regulator. You can see it is almost 12 volt. Okay, so you can see that at input of this regulator, this is the input terminal, we are applying 25 volt, and at the output we are getting 12 volt. This is the beauty of this regulator. Now remember here one important point, that the regulator can allow only 1 ampere of current at the output. Okay, if you try to draw more amount of current, the regulation characteristics will be simply hampered. Another thing that you have to remember, suppose you are using a 7805 regulator. the output will be 5 volt, and at the input you are applying maybe 25 volt. So you see here the voltage drop across the regulator is 25 minus 5, that is 20 volt. And if in such a condition you are drawing a current of 1 ampere, then simply think that this regulator will be dissipating the voltage drop of 20 volt and the current through it is 1 ampere. So a total dissipation will be in the tune of 20 watts, which may be very dangerous. It will be heated like anything. So therefore you have to be very concerned about such things while designing your circuit. Another point is that such type of regulators have got thermal shutdown. If they are heated beyond their capacity, then they will be automatically shut down by their own. You will be having no signal at the output. However, once they are cooled, they will again start operating if they are not damaged, provided they are within the limit of damage. Now you see here such type of heat sinks are used. So you can easily understand that you can find there is a screw. There is a screw here. So the regulator can be put like this, and then you can use simply a nut bolt, fine nut bolt or a screw to attach this metal body. You can see this fin like structure closely with the regulator, so that whatever heat is generated onto the surface of the regulator, that can be easily dissipated with the help of this heat sink. This is what is called as heat sink. Okay, now we will keep everything of the circuit same. We will simply be switching from the full wave rectifier to the full wave bridge rectifier. Okay, so I will put it off. Input of the filter, because I will be simply removing the full wave rectifier from the output. Now you see I will be connecting the transformer to the bridge rectifier, but here you remember that you need not to use this terminal. You can use the center terminal and one of the terminals, any of this terminal, for the connection. So this is the bridge rectifier, and you can see there is the sinusoidal sign. So I can put it here, and other terminal I can simply put here. So one at 18 volt, other at 0 volt. Now I will be getting the output. However, remember here that from this minus terminal of the bridge rectifier I am to take the ground. Now we will put it on, and we can find that we have to find the voltage at the output of the bridge rectifier. We can see here, just a minute, we are getting 24 volt at the output of the bridge rectifier. So they are performing the same operation, there is no doubt in that. However, it depends. If you do not have a center tap transformer, you have to use 4 diodes. If you have a center tap transformer, you can use 2 diodes. It's your option. So now you can see that we have seen the different voltage levels, and now we will be checking the actual waveform by using a DSO. This is a digital storage oscilloscope. I will be using the probe of the oscilloscope to see what is the voltage at what is the waveform at the output of the transformer. For that I will be using the ground terminal and this test terminal. You can see there is a test terminal given. Okay, so I will connect the probe of the oscilloscope like this, and you can very easily see that output of the transformer is actually a sinusoidal waveform. Okay, this is a pure sinusoidal waveform. You can see the line frequencies there, that is 50 Hz, and peak to peak voltage around 20 volts. Oh, sorry, peak to peak voltage you can see here 54.8 volt it is showing. You can see the things here. All right. So, all right. Now you see that we will be seeing what is the output of the bridge rectifier. You can see here I will be simply removing this I will be connecting it to the load. In order to have output of the bridge rectifier, what I will do simply, I will connect it to the load. And now we will be trying to see what is the output of the bridge rectifier. I will be using this terminal as ground. You can see this is half wave rectified output. We will check whether the same voltage is available at the load. So you can see here, even if we change the load, there is no change in the waveform. Okay, so it is half wave rectified signal at the output of the full wave bridge rectifier. Now let us see what happens with the full wave rectifier. So we will disconnect the half wave rectifier from the bridge rectifier from the circuit, and we will simply connect the other terminal, that is the 18 volt terminal of the transformer, to anode of diode D2. The ground we will connect to the load, and output of the rectified section will be connected to the load. That's it. That's a very simple circuit, just to see the output of the bridge full wave rectifier. So let's charge the circuit, and we'll be using our DSO terminals. So ground, and you can see here the output is half wave full wave rectified signal. Now I will be removing one of the diodes. You can see this is purely half wave rectified signal. I will again introduce that. Now what we will try to do, we will try to introduce the filter in the circuit. So I will remove the load. I will put it to the input of the filter. All right. I will connect the ground to the filter, and from the filter I will be connecting the load. So you can see here we have connected output of the filter to the load. Now we will again check at the output of the filter. You can see we are having very less ripple, and let us finally check with the load. You can see here the ripple is so less. So if I simply remove this thing, that is the one of the diodes, you can see there is a change in the ripple pattern. So it's almost a DC right now after this filter. So here there are scope of many further investigations. We can go for load regulation, we can go for line regulation characteristics of the regulators that we have already discussed while doing the experiment with Zener. We can also determine the ripple factor. I am not going into those calculations. My basic objective was to show you that whatever we had studied in our rectifier unit, we have seen the operations actually And now we are very sure that using a full wave rectifier we can have full wave rectified signal, and the same signal can also be achieved with a bridge rectifier. With a pi filter we can get a signal with less ripple, which is almost equivalent to a DC signal, and using a regulator we can have a regulated output, fixed DC output or a variable DC output. So with this much of basic knowledge you can very easily develop your own DC regulated power supply, and that remains as an assignment for you. Thank you for now. For any of your confusions, kindly comment so that we can reach you with the solution.